Hey, hello and welcome to this October 12th and 13th, 2017 SkyTour LiveStream, coming to you from the John Zach Memorial Observatory in northwestern Connecticut. Tonight, it's an exceptional night, and we're very happy to see this. And we're going to look at some deep sky objects tonight, from glorious galaxies to planetary nebula. We'll see them all because tonight it's going to be a deep sky night. There's no moon. As you know, we'll take questions from the chat room, so feel free to participate. And if you have an object you'd like to see, just let Amanda know, our wonderful moderator, and she will tell you. And to those of you who are helping to mod, thank you so much. It's all live, it's all uncut, and let's go. Hey folks, welcome. This is a really pretty night. I'm taking a picture right now. This is the Eastern Veil Nebula in Cygnus, which is more or less directly overhead. And it's a supernova remnant. We've talked about it a few times in the past. And as a supernova remnant, this guy is, several light years across. But it's really an amazing remnant. It has a lot of color to it, and that you can see the blues and the pinks. The pinks are primarily from hydrogen gas that's been singly ionized. That is, the electron has been popped off of the atom, so it's just the proton there. And it has the other color blue. That bluish green is actually a color that's based on a oxygen isotope. And that's something that's interesting too, because we notice that a lot of these nebulae will have these different elements in them. And as you know, as we talked about, supernova are the reasons that we have some of the bigger elements in our periodic table. And this is something that we don't often get a chance to go through in detail. But tonight we're going to do that as we look at a few planetary nebula as well. And of course we're going to look at a couple of galaxies here and there. And we'll see how long it takes for some other supernova remnants to rise. One in particular, the Crab Nebula, comes up later tonight. I'm not sure how long I can withstand the cold, but I'll do my best. And if I can, I will show you the Crab Nebula as well in this telescope. You'll like it. So, this is the Eastern Veil, and they call it the Eastern Veil because it's the side of this roughly circular-looking remnant that is toward the east, as you can imagine. And the Eastern Veil differs from the Western Veil in that the Eastern Veil seems to have been spread out a little bit. As you can see from the top left to the lower right, it's thicker. And the Western Veil is the one that, if you recall, has that spindly look to it. And the Western Veil is just as pretty as well. And we'll see that too. But I wanted to share this with you. This is a 30-second photo at ISO 20,000, which is, of course, the only way to really take a good picture of this, I think. And just to give you a little more for your money, which of course is nothing, I'm going to move us to this other side of the veil to check that out. Alright, so I'm moving now.
Actually, hello chat.
Oh, by the way, hi Amanda. I guess I should have. I forgot to say hey.
That's okay. Just chiming in a little early. No, an interesting question just came up, and I never even really considered asking it before.
Okay.
Ronnie wanted to know if that Veil Nebula is that something we're looking at that's in our own Milky Way?
Yes,
and I was
is.
just thinking, are the only things we can see in our Milky Way, or will the James Webb telescope, will that be able to see things outside of the Milky Way, or I never really...
See, well, we're not really limited by distance so much as brightness, okay? We're limited by the brightness of the objects, and remember the magnitudes that we talked about, the brightnesses of stars and things? I talked about the magnitude system and that how magnitude 0 is fairly bright, magnitude -1 is even brighter, the sun's -26, for example. I think the moon's -13 or something like that. But the thing is, when we look at objects in space, we're not limited by distance, we're just limited by their brightness. So what we need is aperture, that is diameter, light gathering power. And usually light gathering power is a function of how big your mirror is for capturing the light on a reflecting telescope, or how big your lens is at the front end of a big refractor. Refractors, remember, are just lens-based telescopes, and reflectors are telescopes that have a big mirror. Well, the Hubble mirror is about 8 feet across. The James Webb telescope is more than 21 feet across. It's a big mirror, and it's going to be parked out farther away from the Earth. It won't be in Earth orbit. It's going to be farther away. So it's actually going to be in a position where it's going to be able to see things that we just can't imagine being able to see and haven't been able to see. I'm going to just take this picture. That star you see is what's called 52 Cygni. It's actually a star right near the western side of the veil. And the western veil is a very spindly looking, needle looking thing. And it's actually a pretty impressive sight. So we'll check it out and see what we get. And you'll see the camera telling us once it finishes the exposure, then the camera software has to process the image. There it goes. And so now it's processing the image, and it's applying all the corrections and all the changes that I told it to make in the camera, which helps the image look better. Now, one of those corrections that we use is something called noise reduction. Now, noise reduction is something that is related to how the sensor acquires imagery. It could be very sensitive and be noisier. In other words, have a graininess to it. Oh, look at that. That's beautiful. So let's bring that back for a minute. Or it can be a fast exposure, that is only, let's say, a fraction of a second, and have almost no noise. So the longer the exposure and the higher the ISO in particular, the more noise you'll get in the image. Okay, and it's really exclusively an ISO issue, not so much an exposure issue. But if you have a high ISO setting, like I am, this is ISO 20,000, and we did it for 30 seconds. This 30 seconds at 20,000 is actually adding some noise. Where is that noise? Well, let's zoom in and I'll show you. If you take a look, you can see it now. Now the wispiness is kind of in the center. You see it, but look around it. You see this modeling, this mottled look. That mottled look is noise. So what we have to do when we're done taking a bunch of photos like this is we then have to take the end of the telescope and cover it, and then take exposures of the same length at the same ISO and do a lot of them. And those are called dark frames. And they're called dark frames obviously because we cover the end of the telescope. Now those dark frames are then used in processing the what we call the light frames, frames like this one you see on the screen, which are the data. And this light mixed with that dark, the dark subtracts away from the light, meaning you subtract out the data on the dark frame from the light, and that takes out a lot of that noise that you see. When we zoom in, remember this noise we saw, okay, this modeling that you see on either side here, okay, that modeling will go away to some extent. And that's why dark frames are very important. They actually give the software program that we stack several images like this on a chance to get rid of some of the noise and to help reduce that noise. Now, you can do all this processing manually in Photoshop, or you can use a product like Auto Stacker or Deep Sky Stacker, which will stack your multiple images. And if you do that, then you get a certain result. If you want the best result, you literally have to learn, if you want, learn Photoshop and then get your results that way, which is what I do. That doesn't make me better. That makes me actually take a little longer to do things. But if you do it this way, the way I'm talking about with Photoshop, then you get a much better result. All right, and that's kind of what we're after here, is a better result. Now, speaking of results, let's take ourselves off to another location. Amanda, you're still with me, right?
I am.
Awesome.
I just see a question from Ronnie. I'm just trying to figure out what he means exactly by it. He asked, can it capture any moving star? But I don't know if he means like over time, or if he means like, I guess if you took an exposure for long enough, I guess, but I'm not sure.
Well, I'm not sure what the question is, but when you say capture any moving star, stars don't tend to move, but they are moving at all, of course, and they're moving many kilometers per second. But because they're so far away, we don't actually see them. You know, we don't actually see the actual movement unless the star is kind of close to us, like Barnard's star. Now, we talked about Barnard's star. It's basically...
I had a question about that.
Okay, we talked about Barnard's star. It's actually the second closest star to us besides Alpha Centauri. And Barnard's star is a star that actually is moving so fast that it actually moves over the course of a year. You'll actually see the movement relative to the year before. Now, we don't usually get that luxury, all right? But we do see it with this, okay? All right, I'm going to do a 30... I'll hang on to your question for 1 second. I'm doing an ISO 20,000 at 30 seconds of the Dumbbell Nebula. I haven't done a longer exposure like this with this high ISO, so I don't know what to expect. So it might be interesting. It's actually a glorious night. Just beautiful. Now, you were going to say, Amanda, you had a question about Barnard's star.
Yes, I think I saw something, and again, I can't remember the source, so I don't know if it's actually true or not, but it showed a picture and it looked like, I don't know, all these stars. It almost looked like a nebula, like it had like color around all the stars, but then in the middle it was just like a big black hole. It was just like all these stars were missing in this one particular kind of area. And I don't know if there's any truth to that or not, but they said it was in the Barnard star.
Are you saying that when you mean it was in the Barnard star?
Or like in that area.
Wow.
It had something to do with that. I can't even remember where the article is now.
Okay.
But I just saw it and I was like, I would think I would have... It seems like it would have been bigger news, like I would have heard about it from more places.
Mm-hmm.
So, like I said, it might not have been reliable, but did you hear about anything like that? Like, something we've imaged before and all of a sudden now, like, there are missing stars, there's like a black space.
Well, usually a black space typically means that there's either an absence of stars in that location, which could possibly happen, or there is a dark nebula that is farther out that is adding a dark patch to the sky, and that's possible.
Okay, I've never heard of a black nebula before.
Well, dark nebula, certainly a dark nebula. And for instance, have you ever heard of the Horsehead Nebula?
I have.
Okay, the Horsehead Nebula is a dark nebula. That is to say, it's made of dark material that gets silhouetted against brighter stuff in the background, and thus shows up. And by the way, this is the Dumbbell Nebula at 30 seconds at ASA or ISO 20,000 sensitivity. Look at this. There's just a tremendous amount of detail here. But I want to draw your attention to that central star. Okay, you see that central star? That is a white dwarf. Now, what is a white dwarf? A white dwarf is a star that is less than, say, 8 solar masses. That is less than 8 times the mass of the sun. And it's actually the white dwarf itself. I'll tell you in a second. It can't really exceed 1.44 solar masses. Now you might say, well, that's a pretty particular number, and it is, because that's called the Chandrasekhar limit, and I'll tell you what that means in a second. But when a star dies and expands into a red giant, it will eventually shrink down. But when it does, basically the outer envelope, the outer layers of that star slough off and just go off into space. And what's left behind is the hot core of the star. But the hot core of that star is made of a special kind of material called degenerate material. Now that doesn't mean it skips class and gets caught by the police all the time. Okay, degenerate material is actually very different. It's a strange form of matter that comes from being compacted very, very tightly. And because of the nature of the physics, atomic physics, when you compress matter like this in a white dwarf, which basically think of it as it's basically a solar mass, pretty much minimum, you know, 1 solar mass or so, all compressed down to something the size of the Earth. Okay, considering that the sun is 1,000,000 miles across or so, just under that, 865,000 miles across. When you compress it down to the size of the Earth, that material is pretty dense. And so what happens is the electrons in all the atoms of that material cannot be compressed to a certain beyond a certain point without something else happening, and I'll explain that in a second. But up to that point, that magic number, all right, when a white dwarf is being compressed by its own gravity, it has this degenerate surface. The surface material is made of this highly compact material, all right, and it can't shrink any further beyond a certain point because of that pressure exerted by the electrons, and it's called electron degeneracy pressure. Now, what is that? Well, that just means that you have basically, think of it this way, and it has nothing to do with magnetism, but it's a good illustration. Say you had all the north poles of a magnet, several magnets, say 1,000 magnets, and you were pushing them together. They don't want to get close to each other, do they? They don't. They will actually try to repel each other. All right? Well, think of the degeneracy pressure caused by electrons as something akin to that. Again, not magnetism. If you try to compress it really, really, really far, then that pressure will stop you at a certain point. However, if the mass of the star is bigger, that is to say, if that white dwarf begins accumulating mass from a nearby binary companion that we see quite a bit, then that star can be brought up above this magic number limit in mass. That is 1.44 times the mass of our sun. And at 1.44 times the mass of our sun, several things can happen. The star could explode, all right, because most of these white dwarfs are what are called carbon-oxygen dwarfs. They actually are made of mostly carbon with oxygen because the progenitor star, the star that made them, all right, you're looking at the leftover core, and what's left over in the core of these stars like this are some carbon potentially and some oxygen, all right. Now in slightly heavier stars you might get some neon, okay, carbon and magnesium, but the fact is these white dwarfs generally are carbon oxygen. That's pretty much the bulk of these dwarfs. So that said, if material from a nearby star that it's circling, say they're in a binary orbit, streams onto the white dwarf, and the white dwarf accumulates mass more than 1.44, that magic number, then what can happen is something called a carbon detonation. That is, the carbon on the surface, these carbon atoms that are, you know, ultra compressed, can explode, and it becomes a supernova, and that's called a Type 1a supernova. That's Roman numeral 1, you know, I, Roman numeral 1a supernova, and of course they make their own types of elements. Now, if you have a star that's much heavier than that 1.44 to begin with, all right, it doesn't accumulate that mass from a binary. Say the star is bigger, then when it starts to collapse down to where it might be a white dwarf, that the gravity of the star completely overpowers that electron degeneracy pressure I was talking about, the pressure caused by the atoms on the surface, and goes right past it. And that can lead to another phenomenon called a neutron star, okay, or a black hole if it's heavy enough. So you see, that's where white dwarfs, neutron stars, and black holes come into play here. Right? They have to do with the mass of the original star. Now, our sun is destined to become a white dwarf, nothing more, and we don't have a companion star to bleed material onto it. You know, typically that is in like close binaries, but we don't see that there. Here, we look at this white dwarf. This white dwarf is fairly big. It's probably one of the biggest white dwarfs we know of in terms of its mass. And so, you know, this star already died. Okay. Now, if it had a companion circling it, then the material from that companion could stream onto the white dwarf, and then this Dumbbell Nebula that we see here could end up becoming destroyed in a cataclysmic supernova explosion. All right. So it's not like seeing just this one thing, this one nebula, is the be-all end-all. Because if the white dwarf was in a binary system, then something further could happen in this system. In this case, I don't think we have to worry about that. So anyway, that's just a little history of the white dwarfs. I think they're pretty cool. You know, if anyone has any questions about that, let me know. I'll be happy to explain.
Well, I got all excited because everyone from the last conversation, they wanted to do the Horsehead Nebula, but I hear that's more of a winter object.
Oh yeah,
or quite early in the morning.
Oh, believe me, we're gonna try to image the Horsehead ourselves. Yeah, we will. Definitely.
Yeah, because Daryl was saying I might have confused it with Bernard's dark objects.
Okay.
So, are there any we can see? I don't know, maybe not now, but like at some point tonight, or are they all typically winter?
What's that?
I would doubt it.
Any dark
Bernard's
nebulae?
dark objects.
Oh, okay, I know what you're saying. Okay, you're thinking Barnard's star. Okay, actually, Barnard was an astronomer, and besides Barnard's star, you have many dark nebula that are named in the Barnard catalog, and that's what you're thinking about, the Barnard catalog. And yes, the Horsehead Nebula is a Barnard object, so that's not Barnyard, okay, Barnard.
Mm-hmm.
Okay. So
okay, yeah, that's what I was confusing.
That's
so
you were, and I'm glad I could clear that up because exactly so. That's all there is to that. So.
Well, technically, Daryl cleared it up, but that's okay.
Well, Daryl's good at clearing up
Hi,
stuff
Daryl.
for you. I think that's great. Oh, and hi, Daryl. Nice to see you.
Always wonderful. Yeah. Yeah, okay, but he was saying the Horsehead, either it's going to be like really, really early in the morning, late tonight, or it's more a winter object. Are there any dark nebulas we can see tonight, or
I will take a look.
This time of year, or
I will take a look.
Yeah.
We'll see.
And Ian also said that the Flame Nebula was close by too. I don't know close by to what.
It's near Barnard. Is it Horsehead Barnard 33 or something like that? It's right near the Horsehead Nebula, kind of. It's like actually above it, and to the left of it slightly. It's actually very pretty.
And Sigma Ori, multiple
Sigma
stars.
Yeah.
Yeah.
Yeah, those are all in Orion, and we'll see Betelgeuse come up, and I'll put the camera on Betelgeuse at some point when it comes up if I'm not frozen out here. That's a promise. Let me see here now. Let me let's go to say 10 seconds at 6400 here, because this object I just had in here is one that I think you'll remember. We've talked about this just a few minutes ago, actually.
Okay, and it's IC434.
Okay, that's the Horsehead, or is that the Flame?
That's Horsehead.
Okay, Well,
Thank you,
that's
Ian.
the index catalog number. What's the Barnard catalog number? Is it 33?
Oh, I don't know.
Well, then you will find out because Daryl was listening and he'll be happy to tell you.
Oh, Ian actually showed it at the number on that
okay.
one, but
Good.
hold on, I just asked for the Barnard number.
I think it's Barnard.
No pressure, guys.
I think it's Barnard 33, but I could be wrong. That's okay.
Well, it doesn't have to be the Horsehead. I will take any Dark Nebula. I think that would be amazing to see.
Yeah,
so,
Dark Nebula are hard to see in general, because you need a dark sky for them to stand out.
That's what I was going to say. It's hard to see, but it's quite easy to photograph.
Yeah, there's actually some Dark Nebula in Cepheus, okay? In this constellation Cepheus, which we talked about
we were just
before
talking
we got
about.
on the air. All right. Well, let me just show you this. That red star you see in the middle, do you know what that star is? Right there.
It's lovely.
Isn't it pretty?
Very pretty.
But if you notice, it's like the only red star in the area. Isn't that odd? Okay, what we're looking at, okay, that is Barnard's star. That star is moving over 10 arc seconds a year. Now, what's 10 arc seconds? Well, 10 arc seconds is like 1 or 2 widths of that star in the sky. So if you were to do a little measurement and then come back to this in 10 years and look at it, then it would have moved all the way up near the top of this, not the top of the field, but near that other star you see, just above it. Okay, it would move quite significantly. It's moving, well, in this case it's moving up toward the top of the screen here. But it's actually, Barnard's star is really quite the thing. It's 5.9 light years away. Remember, Alpha Centauri, the nearest star system to us, is 4.3 to Proxima Centauri. Remember, Alpha Centauri is a triple star system. You have Alpha A, Alpha B, okay, capital A, capital B. The designations for double stars, they have capital letters, all right? And C, capital C, is Proxima. It's actually a triple star system. And A and B are circling each other. They're stars roughly like the Sun. And C is a red dwarf. That's circling both of them, orbiting both of those from farther out. And that is the Proxima Centauri star that we're talking about. And Proxima Centauri little b is the planet that we found around Proxima Centauri. So it's actually pretty interesting that we've already got the knowledge of this planet around Proxima, because when the James Webb Telescope goes up, maybe they'll look at it and maybe they'll be able to see if there's an atmosphere to go with this planet. And if there is, then that's a pretty interesting development. At least I think so. I could be wrong, but...
Okay, 2-part hypothetical question.
Okay.
And it's from me, so brace yourself.
It's from who?
Me.
Oh, okay.
So brace yourself.
Oh, okay.
Do you know what the first object the James Webb Telescope is going to view?
I don't actually. I actually don't have an idea what they're going to look at first. I have a feeling that it's going to depend on a number of calibrations. It's probably going to look at a calibration object first. The very first object is going to be something it's going to use to calibrate the sensor. Then it will actually look at something else. And I don't know what that first object is going to be, and I wish I knew that, because I'd love to know.
Well, the second part is if it was your telescope after. Well, okay. Well, what would you use to calibrate then, and then where would you go?
Well, it depends what I have to look at. First of all, the James Webb Telescope. Here's the interesting thing about that telescope. This telescope is actually a infrared telescope. All right, it's going to be able to look at objects that are extremely faint, but in the infrared spectrum, maybe they glow brightly, and that includes planetary atmospheres and so forth. So I would probably calibrate it on a well-known infrared star or well-known infrared cloud, And I would get that data from the Spitzer Space Telescope, which was an infrared system. Okay, and Spitzer came after IRAS, IRAS, which is another program for studying infrared clouds and so forth in the galaxy. And the Spitzer Space Telescope is the one that I'd use to calibrate Spitzer objects. Is the ones I would use to calibrate the James Webb, and we'll see what they do. It'll be interesting to hear what they do. They probably already have a plan in place for doing this, so it'll be kind of cool. And then I would actually then turn my attention to the nearest exoplanet I could find, probably the one around Proxima, and start doing a study to see if I could detect any atmosphere. Isn't that a cool idea? I'm moving the telescope, hang on.
Because actually, for once, I actually grabbed a few...
What'd you say?
I was going to say, for once, I actually grabbed a few articles ahead of time, and I think Mark's seen them all. I vaguely kind of glimpsed through. I was hoping he would at least be apprised enough to discuss it. The big radio telescope in China made its first discovery. Can you tell us about that telescope? And
yeah, I actually I'm not sure actually about the discovery, and I need you to tell me what the discovery was.
Oh.
But
Okay.
go ahead, tell me what the discovery was, and I'll tell you what I thought, because I just have to be reminded, because I know they made a discovery. I just don't remember what it was.
It says they used the giant dish to spot a pair of pulsars thousands of light years away.
Oh, yeah,
Heralding
okay.
big things for what is now the world's largest single dish radio telescope.
Yeah.
Back in August. And
Yeah.
I have the numbers here. I don't know if that's going to be... I mean, you wouldn't be able to see anything like that, right?
No.
Even if you were in China with your telescope, you wouldn't be able to see anything like that.
No, because it doesn't matter where you are. We see the same sky ultimately.
No.
We will, but
Eventually, yeah.
Yeah. So I'm gonna take another shot here because I want to see what I can do here to show you something.
Yeah, it says both objects are dense, rapidly spinning stars surrounded by a strong magnetic field.
Correct. That's what pulsars are. Actually, what is a pulsar? I think it merits talking about. In a supernova explosion, sometimes that the explosion isn't even all the way around. Okay, sometimes one side of the star is stressed and pushed and more than another, and what happens is it can induce a rapid rate of rotation in the stellar core that's left over. That rapid rate of rotation can be translated into a huge spin rate. Just imagine a star that's the size of Manhattan Island, okay, spinning literally now, spherically. It's a sphere that's, say 20 or 30 or 40 miles across, right? Miles. And just imagine that thing spinning over 700 times per second. That's how fast some of these can go. And that is really amazing to me. So that's why I'm saying, we really have to basically set aside all your preconceived notions when you talk about the strange universe. All right? Because there are some things in the universe that will just knock your socks off and be literally, absolutely, completely unbelievable. Something that you couldn't possibly, postulate would exist. And that's the rapid rotating core of a star moving that many times per second. Now, they're called pulsars because on that stellar core that's spinning rapidly, there might be some hot spots, that is, spots that are giving off a high radiation, gamma rays or whatever. Those spinning spots are like lighthouse beacons, and only if they flash by us can we see them. And for the most part, there are some that I'm sure that we don't see for sure, many, and then many that we do see. And when we see those flashes, we can actually photograph them The Crab Nebula has a pulsar in the middle of it, okay? And that pulsar is rapidly spinning as well. Now, I want to show you this object because you were asking for it, and here it is. This particular object shows us some dark nebula, okay? You can actually see it. This is called the Iris Nebula, and it's over in the region of Cepheus, okay? It's actually just above, it's in Cepheus, and it's right above Polaris right now, above the North Star. Do you see this object? This star is a hot star, but it's actually it's doing multiple things. The star is illuminating the cloud, and the outer part of the cloud is actually just you know, a reflection nebula, right? Because it's that bluish color. Some of the blues induced by the filter I'm using, okay, but for the most part, the blue color of that nebula belongs to the fact that the star is causing this to be a reflection nebula. That means it's not hot enough for it to actually ionize anything in here, but it's not impossible, and it does do some ionizing elsewhere, okay? But basically, we're seeing something else in here that you can't really see in this photo, and some of the nebula will look red, all right? Now, you'll say, oh, well, I know what Mark told me before. That means that it's hydrogen gas. It's that ionized hydrogen causing that stellar nursery thing to go on there. And in fact, in this particular case, like many things in astronomy, you'd be wrong. It's actually because there's so much dust in this particular region that we're seeing something called interstellar reddening. It's the same effect of the light that's being reflected is blue near the star, where the star is, okay? But as it goes through more of the interstellar dust, it starts to look red in the same way that our sun looks red at the sunset. And now I know that the red sunlight is not the dust, but think of it this way. The light coming from the sun is white, and as it gets to us, some of that light is scattered by the molecules in our atmosphere. That scattering process is going on here in this nebula as well. So the sunlight that is in that star is being scattered to the point where what we see for the final light coming to us is the red, like the red clouds you see at sunset, all right? So that's why it looks red, all right? Now you can see a little bit of it just below the star. You can see a little bit of that red down below. And there's certainly more of it to the outside. And in a darker sky, we'd actually be able to see the full extent of this nebula, which is, it goes out to just about the zoom frame, which is there you see in the lower left, and just about halfway in from the left of the time at the top. So it's a little bit more extensive. But you see, just above the star, you see that dark lane? There's that dark area right there. And I can show you that in particular if I can move it. So now I have it right in the center. Just above the star, you see this fairly well contrasted dark area. That's a dark nebula. How do you know? Because it's being silhouetted against the brighter nebula behind it. This region actually in Cepheus has this bright nebula. And you asked if there were any dark nebula that we could see. And here's your answer. Yes, we're seeing one right now. Okay? Does that help you?
Oh, no.
It doesn't help you?
No.
Why?
I don't know. Hold on, that's a lot to take in. I'm thinking.
Well, you had asked if there was, you know.
No, I know, and I appreciate it. I'm trying to get my head around this, but this is like a brand new concept to me. Okay, so what?
What?
Okay, so is there always one bright star in the middle of a nebula?
Well, a nebula is illuminated by something, okay? And that illumination has to come from something that's typically a star, or more than one star, okay? For instance, let's go to another object that...
I mean, maybe I don't know enough about nebulas to be you know, really spotting the difference between a regular nebula and
Well,
a dark nebula. But like, I mean,
but look at this. See this on the screen here? You see the star in
okay,
the
well,
center?
the dumbbell's a nebula.
It's a
Is
planetary.
illuminating that?
Because of the fact that the dumbbell is actually a dying star remnant. All right, because you have a star in the center that's a dead, a dying, white dwarf. Remember, white dwarfs don't have any nuclear fires anymore. They're just bright and emitting from their thermal radiation that they have that they're giving off. That's it. There's no more fusion going on in a white dwarf. Okay, so what we see.
But what we're looking at now
we're seeing
is
a
not a
regular
white
star.
dwarf. Yeah. Okay.
Okay,
But
just
it
above
will.
Just above it, there's a
Eventually.
dark nebula. See that dark area just above the star? That's actually a nebula. It's actually a dark dust between you and the bright spot behind the star, the brighter nebula behind. Okay, and we're seeing it silhouetted. That's what that is. Okay, it's a very cool thing. Now, I'm not sure if this will actually work now. Might be too low to see.
Yeah, this is definitely an episode I'm gonna have to listen to back a few times.
Well, I'll be happy to explain it a few times, but before I do that, I'm going to try going to something else. Hold on. Oh, we might just luck out. We might just luck out here.
Crossed.
Huh?
My fingers are crossed.
Yeah, well, I'm just trying to show you another nebula that we could look at. Now, we just saw the Iris, okay? And now what I'm going to do, I have 16% on that battery. What I can do here, okay, just got to move over a little. I can barely just...
Iris. And what was the Dark Nebula? What was that called behind the Iris?
Well, no, that was part of the Iris. That's just a detail within the Iris. Okay?
Oh, okay.
All right, so let's now do, we're going to do a 30-second I'll go for 20,000. 30 seconds at 20,000 for this object. And let's see what happens. That'll give us 30 seconds to talk. What are we doing? We're actually taking a picture of this now. This is the Eagle Nebula. A number of you are familiar with the Eagle. We've looked at it many times in the past. Now, the Eagle is a star-forming region. The Iris is an area where there's a lot of dust, but the star is not hot enough to ionize the hydrogen gas nearby, but we're getting that reddening. Remember, it takes very, very high temperatures to ionize elements. So that star doesn't give us the high enough temperatures to do that. But in the Eagle Nebula that we're looking at, or coming up here in a few seconds, if it came out, let's see, hope it did. I was tromping around in the observatory, so hopefully we'll see if my dampening field is in effect. The Eagle Nebula is a place where stars are still forming, and there's a lot of areas of dark nebula within the Eagle. All right. Oh, there it is. Holy cow, that's beautiful. Wow. Wait until you see
Okay,
this.
you know what?
Yes, what?
Okay. Ooh. I don't know. Maybe it's just, I don't know. It's probably my overactive imagination. Is the red part supposed to be the Eagle? Or is it the white stars in the middle?
No, that's a cluster that's associated with it. But, okay, this is another case where you're seeing a dark nebula. Okay, but now you can see it more easily. It's right there about the center. It's a little spindly thing going from upper left to lower right. Do you see it? Kind of right near the center. Let me see if I can get it over a little more. See if we move us over a little more. Oh, I can't. Oops. Unable to magnify. Okay. Hang on. Oh, come on. Just a minute. Okay, here we go.
Huh? Family photos?
No, actually, that was the SkyTour LiveStream meeting I had here on the front lawn.
Oh,
Okay.
nice.
Yeah, that was actually not a live stream. It's actually a mutual UFO network meeting. Okay, there we go. Okay, now, just above center, you see that dark, looks like a little tornado, right? That little dark nebula right in the middle there. Okay, and it kind of goes off to the top a little, off to this farther. It's on a diagonal. It goes from the upper left to the lower right of just above center. Do you see that?
I must be looking. I mean, I see a very noticeably dark.
Yeah, that's it. Okay, that noticeably dark thing is the dark dust within that nebula. Okay, within that whole thing. Now, if you look to the lower right, you see those stars down there. Let me see if I can get ourselves down there a little more. Okay, those stars down there are younger stars that were formed in this cluster. Okay, in this nebula. All right, as a cluster. So this is a stellar nursery. Now, you'll say, well, wait, don't stars form within gas and dust? And yes, they do. Well, then where's all the gas and dust? See, around these new stars here, you see, well, where's all the gas and dust? It was there, but after they formed, they have stellar winds of their own, and they blow a lot of it away. They send a lot of it away with their radiation. So that's what we're seeing there. Now, to the upper left now, where that dark nebula is, this is still a region. And those are, by the way, remember, these are the pillars of creation that we saw the Hubble shot for. The pillars of creation here, right there in the center now, those are actually very much a centerpiece of the Eagle Nebula. And they're an area where there's these little globules that are formed. They're self-gravitating matter and material that's like forming little blobs. Maybe those blobs will become whole solar systems someday, and maybe there'll be a star that will form in there, and then that might actually give rise to a circumstellar disk of material that could then form planets. We see these globules in Orion. We see these globules all over the sky in the southern hemisphere Milky Way. We see them in the Magellanic Clouds, which are the small companion galaxies to our own that we see out there. We can't see those Magellanic Clouds from here, unfortunately. But this is the Eagle, and now it's, again, these are, moment-to-moment shots that we're taking, so clearly there's no processing going on other than what I instruct the camera to do as it takes the shots for us. See? So that's a really interesting development there. Now, one more that I want to go to that we've seen before, but I'm going to go there now anyway. This is another one that we're going to, and I'll show you why we're going there in a second. Okay. Now, first of all, let me make sure that I've got it in here. Let me do an acquisition shot. I believe it's probably going to be in there, but I'm just going to do this anyway. So this is a 4K acquisition. Let's just see what we got. Okay, there it is. It's over on the right-hand side. So what I'm going to do is just move it into the view. Okay. This is very low to the horizon right now, just so you know. Okay. There's another cloud of gas and dust that actually has some dark lanes within it, some dark areas as well. And we'll do, let's do, for purposes of just showing you some photos of this thing, I'll do in ISO 40,000, but not at 30 seconds. Let's do 13 seconds at 40,000. It'll be somewhat grainy, but we're going to be looking at this just to, again, it's sort of low to the horizon, but a little bit lower than the Eagle was. But I want you to see this too, because this nebula that we're looking at is something called the Omega Nebula. And the Omega Nebula is another region where we think there's a very different thing going on. Now, we just looked at a reflection nebula, which was the Iris. Okay, and we looked at a star-forming region with H2, that is singly ionized hydrogen region, where star forming is going on, and that was the Eagle. And now we're looking at the Omega, which is not too far away from it. Okay, but it's really pretty actually. If you notice the Omega, you see there's stars that are causing the Omega Nebula to have excited atoms as well, so that we get ionization going on. So this is, an H2 region. However, we think that maybe, astronomers think maybe, that this region might be done doing star formation. And now what's left is going to basically evaporate away as the stars within, some that you can and can't see, are actually blowing stuff away. However, look down here, okay? You see that object right in the center, that round black area? You see that?
Mm-hmm. Yeah.
That is a dark nebula, okay? Another one. So you're asking if we can see dark nebula. The answer is yes, almost everywhere we look. And Lagoon Nebula also has dark nebula. Lagoon's already set, so we can't really see that. Well, actually, it hasn't set, but it's behind the trees, so we can't see that. But see, this is a dark area as well. And this is something very interesting because this differs from things like a supernova remnant, like the Veil that we looked at earlier. The Veil doesn't have any dark nebula, does it? Okay? That's because when the star explodes, it doesn't tend to blow out dust. It tends to blow off gas. And that gas and other elements that go with it will, of course, come off and be potentially excited by stars that's near, or it'll have a residual heat that's it's still giving off energy from that will cause it to be ionized and stay ionized for some period of time. So that's very different. Remember now? No, but a supernova remnant, just like a planetary nebula, those are both the results of dying stars and dead stars, right? Well, they're also showing green and red, right? Remember the dumbbell? It shows basically a green hourglassy thing, and it has some red fringes. Well, the red is the singly ionized hydrogen, the H2 regions, and the Veil Nebula. Sorry, I was just looking at something. The Veil Nebula is actually a supernova remnant, so it actually looks a little bit different. Okay, it has a filamentary structure to it, and it's much more extended, and we call that distended. Okay, it's a distended object, and that's because of the fact that the supernova is a far more cataclysmic, thing, a cataclysmic event, and this, blows stuff out into space at a very high rate of speed. And the Veil is still expanding. I mean, now there are points where the Veil collides with other interstellar media out there. For instance, if the Veil, there's a part of the Veil that's intersecting a dark cloud, that is a dark area where there's dark gas and dust, and it will cause it to emit on different frequencies. It'll excite the atoms in there and cause them to basically do that emission, and it'll become a little bit of an emission there. All right. Same thing with dark gas and dust, or the dark dust. The dark dust can be pushed up into basically like a bow shock, like a shock front. Think of a wave in front of a boat. As a boat's going through the water, it's piling up the water in front of its bow. Same thing happens with a supernova. It piles up like a snowplow. It piles up stuff in the interstellar medium as it goes through. That piling up creates new elements as well. So as it's piling up these things, it creates new elements as well from that compression and the heat generated from that. It's cataclysmic, and it's the biggest cataclysmic it's the biggest cataclysm that the universe has to offer, besides the Big Bang itself. So that said, we've kind of taken a tour of the different kinds of nebula. We saw the Iris Nebula, the Reflection Nebula. We saw the Veil supernova remnant, which was a supernova remnant, the remnant of an exploded star. We saw the Dumbbell Nebula, which is a planetary nebula, the remnant of a star that didn't die as violently and left something behind, like a white dwarf that we could see visually in the center of the nebula. Okay. Similarly, there are more objects like that out there, like the Dumbbell in particular. All right, and there's a lesser known object that I'll try to locate for us after. That will be fun to look at. But right now I want to go and find one more planetary for us to look at, the one that we've seen before, but that, with our new understanding of nebulae, maybe that'll be better for us to talk about. So here we go.
So, and I hope this isn't asking you to repeat yourself, because I mean, there's only so much I can take in, and then, you know, I get lost and confused. What is it that... Well, you said some nebulas were, like, dust, and then some were, like, reactions.
You know what? That's a very good way to say it, actually. That's a good way to say it. That's a very, very good way to say it. You're right. Some are the result of just, you know, the illumination of dust. Okay, for instance, there is a nebula around the Pleiades stars, and that nebula is blue. Now, that's because where the Pleiades are is a very dusty region. But you'll say, well, wait, if the Pleiades formed there, where's all the gas from which they formed? Isn't there still gas there? Well, if there is, there's not enough. And the Pleiades are hot young stars. And remember, on our OBAFGKM scale, they're B stars. Okay, so they're fairly bright next to O's, which are the brightest and the hottest. Okay, so they're the next ones. And the B stars of the Pleiades, all right, they illuminate a lot of the dust around them, and that causes a blue reflection nebula. And if the Pleiades are up, I will show you. And we'll actually image some of the nebula a little bit. Now, for this one, okay, I will do, and for those of you that are sharp and quick-witted, you already saw what the object was. Okay, so I'm going to do 13 seconds at ISO 5000 right here. I have to tell you, I guess, and maybe you can tell me what you think, folks, but I really enjoy just taking this camera and pushing it to its limits. And that's exactly what I'm doing. I'm pushing this to its limits. Now, this is, of course, the infamous Ring Nebula. And when I say infamous, I'm only kidding, of course. When you look at this nebula, all right, the first thing I got to say, there's a reason why I call it infamous. It's called infamous, to me anyway, because of the fact that the Ring Nebula is basically one of these places that's really, it's notorious because we don't really know how far away it is. You know, we have estimates, some good, some bad, okay? So the bottom line is that this one here, okay, is a ring in name only. It's not actually a ring, all right? And you know, it's actually a sphere. And I've mentioned this a few times, but I think it's important to understand. Okay, now we think it's about 1,400 light years away. Okay, but again, they're kind of difficult to get the distance to. All right.
Why?
Huh?
Why?
Because as a when we get distance to stars, okay, we rely on things called variable stars. Okay, we use Cepheid variables for some. We use RR Lyrae variables, they're called. And what happens is there's a relationship where the period, that is the change in the brightness of a star, okay, is a direct reflection of how much mass that star has. And then there's a relationship to its brightness. Now, we can gauge how bright a star is, okay, that's called a magnitude, and we get an apparent magnitude. If we know the mass, that is how bright it looks apparently in our sky. When we get the mass of the star, now we can get other details of the star. We can get the radius. We can get the distance, okay, because we can calculate something called absolute magnitude. And then when we have absolute magnitude and we have the apparent magnitude, it's all done. Now we have all we need to calculate the distance to the star. There's a formula, and it comes from a special relationship called the mass-luminosity relationship that we discovered when we looked at many, many stars that vary in their brightness. It turned out that the period of the brightness change, like if it brightened and dimmed by over 3 or 4 days, and had a certain brightness that we can measure an apparent brightness, then all we had to do is go to a special table. It looked like a linear line. It was like a line. And just plug in the apparent brightness, okay? Plug in the apparent brightness and get the what's called the absolute magnitude. And then from the absolute magnitude and that apparent brightness, we can calculate its distance. And then we get the radius of the star, the temperature, all these things. temperature, of course, can be derived from looking at the luminosity, that is the intrinsic brightness of the star. I'm not expecting you to just take all this stuff in, guys, and just like say, okay, I understand, let's move on. I'm just trying to tell you how there's relationships that give us the distance. Now, with a nebula, there's nothing in the nebula that can give us its distance, okay? We have to rely on a property of the star itself in the center, or we have to rely on other nearby objects to see what they are. But the Ring Nebula is one of these objects that doesn't have a very definitive distance, but that's okay. Over time, you know, we'll get better at this, and maybe even with the James Webb, we'll be able to figure this out.
Well, see, because that's what I was thinking when you were saying that. I was like if it's so exact that you can work these things out, it should apply to everything. But then I was thinking, like, what about a dying star? That mass is going to change, changing all those dimensions and stuff that you're looking at, the brightness and the luminosity. So, but that doesn't mean it's getting closer or further away.
No.
Is that the problem, because the mass is changing in nebulas?
Well,
Or because sometimes it's dust and there is not enough mass to calculate? Like,
in very dusty regions of the Milky Way, we have trouble sometimes calculating how much reddening, like we saw in the Iris Nebula, is actually going on there. And that can change our estimates of distance and magnitude, the brightness. And a small change in that brightness can correspond to a very large distance error. So we have to be very careful. So if you think about it, if you think about it, when you look at this particular nebula, the Ring Nebula anyway, you can see the central star there. Okay, this particular central star is again a white dwarf, like we saw in the Dumbbell Nebula. It's actually a little different of a this one is I think made from a slightly smaller progenitor than the Dumbbell Nebula was, and it's basically that central star here, though, is 1.2 solar masses. Okay, that white dwarf in the middle. So what that tells you is that it's actually pretty close to the 1.44 cutoff, where it will then do something more. However, there's nothing else that can happen here because it's not a companion star. It doesn't have another star nearby. So it's basically it's just the ultraviolet energy that comes off of this white dwarf, which is so powerful. And again, it's just the thermal energy left over from all the processes that went on in that core that it's illuminating and causing the emission in oxygen 2, which is that O3, which is the doubly ionized oxygen that you see, the blue color, and the slightly red to the outside in hydrogen. And there's more elements in there that can be picked up too. There's a whole host of elements that are in these nebulae. I'm just giving you the overall view. Now, here's an interesting thing. We look at these things and think, oh, they've been there forever. Not so. The Ring Nebula is actually, it's actually only about 6,000 years old. So the Ring Nebula formed, I think it's actually between 6,000 and 8,000. 6,000 and 8,000 years old. So that means that there was just a star here before that. And had there been a telescope at the time, we could actually see just the star, and actually been able to see what kind of star it was. But the stellar core in that star, after the sloughed off outer layers formed, basically that's all that's illuminating the nebula. And over time, perhaps in about a million years or so, maybe that star is actually going to cool off. It's actually going to take it over 1 billion years to cool. And then it'll be a black dwarf, and the elemental excitation that's occurring in the atoms of this cloud surrounding the star will go away, and it will become an invisible object in another 1 billion years. It'll just be a dark ring. It's actually, yeah. I remember talking to you about this and talking about how this is a sphere that we're looking at through a thin layer on the front and the back. So, and the side you're looking through more of it.
With the hand analogy, yeah.
Right. Yeah. But if you look at, remember I mentioned if you hold your hand to the side with your fingers spread apart, okay, you can't see through your fingers. But when you look at it from the front or the back, you can see through your fingers. That's sort of equivalent to this. And that still holds true, but there's one little wrinkle, and that is that the thickness of that ring is too thick for it to be a shell that's a spherical shell. And I'm referencing some recent research here. The actual nebula itself isn't so much a sphere, but more of a it's more of a toroidal ring, so to speak. So in other words, it's actually not perfectly spherical. It's actually coming out towards you a little bit and going into the screen, so to speak, a little bit. Kind of like a...
I don't want to say cone-shaped, but...
No, more like a tunnel.
A tunnel.
Okay. Yeah, kind of like a tunnel, in some sense. You know, so it's actually pretty cool. How this, you know, it's basically, they're basically saying it's actually like a torus and not a spherical shell after all, and that's possible. You know, its overall shape might be that of a cylinder, okay, or an hourglass, which we just happen to view, you know, kind of just a slightly off one pole or whatever, because maybe we're actually seeing down from the top of the star, for instance. So you know, it's actually an interesting nebula that we're not able to, you know, decipher as we thought we had. You know, and that's just, and I've told you that it was a spherical thing, but in my journeys and looking at more of the research for the nebula, I discovered that it's actually more of a torus. You know. And again, like an hourglass, so it's lengthened maybe out of the screen and into the screen, which is kind of cool. Just a little different, because my hand analogy still holds, though. You're looking at less material at the front and the back side, and as it turns out, the north and the south pole side. Okay, so maybe we're looking at the south pole or the north pole here, because the thinner material probably is likely going to be perhaps at the north and south poles. But it's just a interesting nebula nonetheless.
And that's why you have to subscribe and hit the bell, because you got to stay up to date on these kind of things, new developments in space.
Yeah.
That's awesome.
Well, isn't everybody that's in the chat subscribed? Maybe, maybe not.
Well, there could be newcomers.
Sure.
I mean, to subscribe, that's one thing, but there's a little bell right beside the subscription button, and if you hit that, you'll actually get notifications when Mark brings us their next all-new, all-live SkyTour LiveStream.
Exactly. Exactly. Boy, that's well done.
Yeah, okay, listen. What do we have any stars that we know are going to die relatively soon? Like, maybe not in our lifetime, but I mean, like, not like in a million years from now. And if so, now that we have the technology, if we could see the star, could we watch a nebula being formed?
Yeah, we actually did that, believe it or not. In 1987, with supernova 1987A, there was actually a explosion of a star in the Magellanic Cloud, and we actually saw the light echo coming out from that supernova explosion. What's a light echo? It's the light moving out and illuminating and affecting the gas and dust at a distance away from that explosion. We actually saw that, you know, and that was a brilliant thing. You can actually look it up. Look up the supernova 1987A light echo and check it out. It's really cool. I'm going to head to another object right now, which may not be visible.
Supernova 1987?
Yes.
A. Ooh. Video?
All right, 1 second, guys. I'm moving the El Telescopio. Take this telescope around here now. And I'm going to check out this object because I want to see if I can see it. Alright, so there's the general location. And I'm going to just do a... I'll do 13 seconds at 12,800 ISO just as basically a finder shot just to check it out. At this angle I have a lot of wind coming into the dome, so it tends to be chilly when I look toward the north here. But I did put on wool socks, and I have a hat that wraps around the bottom of my chin, so I look like a redneck right now. Oh, I don't see it. Let me go back and... I mean, I could just... Oh, I see it.
I saw an interesting little picture, or little video, but...
What's that? What do you mean?
Oh, the 1987A?
Oh, yeah.
Yeah. One looked, I don't know, kind of real but kind of weird, and then the other one, I don't know, kind of looked like CGI to explain it, so...
Yeah, maybe one was in false light, you know, it was like false color, they're called. It's possible.
But, okay, so... how did they know?
Well, they found it.
Was it just luck that they happened to find a dying star and just
they found it and
watched
when they saw
it, or could they actually time it that it'll be maybe around this week or something? How close could they time when it was going to happen?
They couldn't, and there's no way to time that. You know, we can't tell when a star is going to go supernova on us. You know, we can't time that. We can't tell.
If you just luck out and find a dying star,
yeah,
keep watching forever.
Yeah, well,
until something happens.
Well, Betelgeuse is gonna go supernova on us at some point, and that's Orion's main star. You know, the brightest star in Orion, Alpha Orionis, and that's gonna explode. At some
and
point.
what happens then?
Well, nothing will happen.
Well, nothing will happen maybe to us, but what'll happen to, I don't know, the constellation?
Nothing.
Nothing?
No, the stars are all very far from each other. They're not going to have any impact on each other.
Is there going to be a nebula in the middle of the constellation then?
Ah, now that's a good call. I have a feeling we're going to end up in that far future. Someone will actually see a very, very prominent supernova remnant around Betelgeuse.
Okay, so where is Betelgeuse in approximation to Orion? Did you say, is it one of the stars in his belt? No.
No, it's the top left red star. It's a red supergiant in Orion. The only one. It's really cool.
See, I'm still thinking of it as a constellation. Would that be like his left shoulder or something? Or I'm trying to kind of visualize if I saw the constellation where to look.
That would be his right shoulder.
His right shoulder.
But I mean, you know, from his point of view, okay? It would be a left shoulder. It'd be a left shoulder for you looking straight at it in the sky, for sure. Yeah, okay, there we go. We got a little guy down there. How am I going to get that? Which way is it going here? Let's see. Can you see any of these?
Oh, and that reminds me. Slim Dunks had a question from earlier about the James Webb Telescope.
Yeah.
He said, I'm assuming it's he, sorry. Will the telescope give us better views around the center of our Milky Way?
In the infrared, it may. I mean, we're going to end up having quite a bit of dust and so forth there, so it might be pretty cool. You know, again, it's an infrared telescope, so it's going to be look at the residual heat left over from everything that's going on in the center of our galaxy, which we can't see actually. We can only see kind of near the center of our galaxy. So it's pretty interesting, you know. But it may. I I can't predict. I can't tell you because I don't really know. You know. I don't know how it's going to
Yeah,
show.
but sometimes theorizing's half the fun, and
Oh yeah.
eventually a theory is going to be proven to be right. I mean, that's
Oh,
kind of the
maybe.
point, right?
Maybe.
Yeah.
I mean, the theory that the Earth is going to be destroyed by the sun someday will be correct at some point in the future. You know? I can't imagine why people aren't a little bit more worried about that. You know? Because that's we got to plan for that. That's, you know, it's a few billion years away, but, you know, it's not that long. Actually, it is. I'm just lying. I'm messing with your heads.
No, but I mean,
Mm-hmm.
I don't know.
This nebula I was looking at isn't working out, so I won't look at that. There was another one, though, that is nearby that I did have better luck with. I wanted to see if I could catch it. Alright. Alright, but, you know what? No journey here is complete without actually going to this next object here. We're deviating from nebular stuff for the moment. Let me just get us over to this.
No, see, I mean, and it's so weird because, I mean, I don't know. We've seen the Pillars of Creation in the Eagle, and we've seen, I don't know, we've seen these things so many times, and I don't know how I couldn't have known that we were looking at dark nebulas in
Because I've never
regular
mentioned
nebulas.
I never mentioned
I know, but, well, why not?
I just didn't.
Well, you pointed out the dark spots before. I just, you never ever
Yeah, I
used
haven't.
that term. That's weird.
No, I didn't. But that's okay. I mean, it's time.
It's time, yeah, wow.
It's time to mention it.
So when a star dies,
Yep.
it, oh my god, I hope I say this right. It doesn't necessarily go supernova, or does it? Is that what the explosion's called?
It is, but that's not that is exactly right. It doesn't necessarily go supernova. You're right.
Okay, but if it's a star, it will turn into a white
If it's
dwarf?
if it's a star that's less than say 8 masses or so, of the sun, it'll probably become just a white dwarf. Yep.
Okay, so if it doesn't go supernova, what happens? There's still some kind of an explosion, though, right? Some kind of... Is there?
No, if it doesn't go supernova, then you get, well, like the Dumbbell Nebula, or you get the Ring Nebula. You get a Planetary Nebula, where the outer layers of the star just slough off into space as the star contracts
Okay.
internally, leaving only that core of material that's hot, and that's all you get in the end. This object we're looking at here, okay, this is actually in the 4K mode. This is a live view, so you see when I bump it, you can actually see it moving. This is actually the double cluster in the constellation Perseus. Okay, and this is a beautiful cluster of stars. It's a double cluster, which you think, wow, how can that be? It's amazing that they formed here. But there was probably a double lobe of gas that these formed in this region, and I can't, for the life of me, I can't figure out, you know, how that must have looked. You know, I mean, I get it, but man, what a unbelievable turn of events that you have this beautiful gem in our sky. Is that not true? And now, just to be complete, what I'm going to do, if I don't run out of battery power here, at 4% now, I got more batteries, don't worry. Don't worry, I got more. I'm going to do I'll go down to 25,600 and do a 15-second exposure and see what we get. So this is 25,000 at 25,615 seconds. This cluster of stars, this double cluster, is actually 6,800 light years away. Isn't that amazing? 6,800 light years away. And now, if you wanted to, knowing that magic 206265 number I told you, if any of you remember, you can figure out that with the 18 arc-minute diameter, okay, you can figure out how big in light years that is across. See, I like to give you some practical astronomy.
Ooh, speaking of which,
Yes?
there was... hold on. I'm finding another article that I sent.
Okay.
Astronomers just set a new record for measuring distances across our galaxy.
Yes.
Did you see that one?
Yes, and the way that they did that, that's what's interesting. This article, guys, I was talking about how the distance metrics that we use have traditionally been limited by the fact that we can't actually see the motion of the stars very well. What does that mean? It means that we don't get the parallax. That is, when you hold your finger out at arm's length, I've talked about this, and you close one eye, and you put your finger in front of a vase or a picture on the wall, and then you close that other eye and open the one you had just closed, you'll see that it looks shifted against the background of the wall. Okay, your finger is shifted against the background of the wall. That shift, if you think of the distance between your eyes as the orbit of the Earth on either side of the sun, and that shifting object, the finger that you have extended, okay, that finger is a nearby star. And the vase and the picture on the wall is actually the farther stars. Then that's parallax. I was actually doing parallax study when I was getting my degree. I actually did a lot of parallax photos in the big Van Vleck Observatory with a 20-inch refractor. And this was an amazing thing, because we can actually detect stars distance out to a certain distance, okay? And the trouble was, it basically fell down at the point where you didn't have any ability to accurately gauge the small, tiny distance that the star moves, because the farther away from the Earth the star is, the less that motion is, even with the motion of the entire diameter of the Earth's orbit. So what do? Well, what you do is you have to get a better way to measure the movement of the star. And what they did was they used something here on Earth called the VLBA, the Very Large Baseline Array.
These names, oh my gosh.
I know, astronomers love acronyms. And
the Very Big Telescope.
Yeah, the Very Large Baseline Array. And the Very Large Baseline Array basically is a bunch of telescopes around the world that together, their imagery can be combined to make one object, to look like one object. All right? What's that do for us? Well, that gives us the opportunity, you see, to actually get far better accuracy when we are doing parallax measurements, meaning we can get parallaxes out now to 60,000 light years, which is something we couldn't do. The record was like 30,000 just a couple years ago. And now we're doing even better. And so they can actually gain the distances to these farther objects and actually see farther across our galaxy than ever before and accurately gauge distance. Now, our galaxy is about 100,000 light years across. So being able to see across the diameter of our galaxy to some distant objects is a real feat of engineering. And I'm very, very impressed with that. But that's the Very Large Baseline Array is responsible for that. And it's not just quick stuff. You know, this takes a lot of work and a lot of effort. You know. Now earlier, when you mentioned actually, Amanda, that you wondered whether we could actually see, you know, beyond our galaxy. Well, we can, and I want to show you an example of how we can do that. Okay. Because right now, right, the object that I'm closing in on, which is a really bad object to have here because I'm so, you know, this perfect spot for me to get freezing. I'm working
the sacrifices you make for us.
I don't know, I'm just get cold. Okay, there we are. Now let me just move this up. Okay, now this object you see, okay, and there's a reason why I'm putting it like I'm putting it, okay, I'm putting it kind of off to the edge like that. I'll show you why, if I'm right. So this is 160,000. I'm just going to drop down to 64,000, which is still quite high. And I'll do 20 seconds at 64,000. It's just a foundational shot, just to kind of give me an idea of what I'm looking at. I'm loving the night, by the way. This night's beautiful. So before you guys came on with me, I had actually done about 10 shots of the Eagle. And the 10 shots of the Eagle are going to be used to make a very nice composite after to show you. It'll be up on the SkyTour LiveStream companion site. So what I want to do is show you that, and I'll do that as soon as I get off here, which might be sooner than later, because I believe that we've gone an hour and a half now. Here we go. Okay, this is the Andromeda Galaxy, folks, once more. And you can see, when you look at the Andromeda Galaxy, look at all the dark lanes you see just above the central nucleus of the galaxy there. And actually just out from that center bright spot in the nucleus of the galaxy, you can see a very a very fine filamentary line there. And then you see a much thicker one. Those are the equivalent of Dark Nebula. But this is a galaxy that's 2 million light years away. This is not in our Milky Way. All the stars you see in the field there, the bright, discrete stars, those are here in our galaxy. And we're looking through them an additional 2 million light years more distant to see this galaxy. So here we are looking with this small telescope, and I'd say backyard telescope, but it's a front yard telescope here. All right, and this telescope is actually seeing the Andromeda Galaxy's detailed nuances quite easily. Now you can also see that I'm using at this brightness, I'm sorry, not the brightness, but at this ISO setting, you can see the color modeling and stuff that occurs with high sensitivities. Now, to do a more realistic shot, this was 64,000. I would drop it, say, to 12,800, and say do a 20-second. And then I'm doing one now just to show you what the difference is. But then what you do is you combine 25 of those shots or 22 of those shots, and you stack them together. And over the stack of those, you'll get a shot that's better than the one we saw that was at 64,000 sensitivity, and it will actually have a much better response in the noise arena. So you'll see now. Compare that modeling as we'll do actually in a minute. You can compare the modeling of this one to the modeling of the previous one. It's modeling, M-O-T-T-L-I-N-G, modeling. You know, the modeled color and shape. So now look at that. That's a little bit more reasonable when we go to this, okay, and we compare it to that. Yes, this looks brighter, but guess what? If I do 50 of these or 25, keep doing that, do 25 of these, okay, as opposed to 25 of those, all right, this one will actually produce the better result. And the reason for that has to do, of course, with the fact that we would end up getting a far more detailed, less grainy view at the end than we do with this previous one. Also, look in the center core of the galaxy. See how you see that bright spot right in the center? And you actually have some detail around that would be lost with this other one. This other shot here, okay, when we go back to that, okay, if we go back to this and we try to look at, I keep doing that. We go back to this and then where'd it go? Okay, we go back to this. Okay, no, I thought I was losing my battery, but I'm not. Okay, hang on.
Just your mind.
I'm losing my mind, yes.
Mm-hmm.
Okay.
No, but I know what you mean. It's bright, but it is grainy.
Yeah.
You know, so it's. I mean, there's not really much benefit to putting a whole bunch of them on because it'll just look too staticky, right?
That's right. That's correct. And so we're going that way. Got to go this way. Okay. So once again, so this one now, if we zoom in on this one, you see the modeling. Remember that? Now, all those dark areas in the galaxy that we see there, they look good from a distance, but when you get up close, they look crappy. Same you know, for any other type of thing you do with that. Okay, if you actually do this though, if we go back to say this image, see the difference now? It actually looks better. Okay, and that image, okay, has some modeling, but guess what? It's more subdued, and that value of the nucleus, look at that. That detail within the nucleus of the galaxy is still preserved here. And if it's there, we can preserve it on the other images that will come from it. Okay, in this one, what I was trying to show you before, this one, when we look at this one, all right, this nucleus is just blown out. You can't get back data that you've lost, all right, and this data is lost. It's bright white. There's nothing to see here, folks. Okay, it's just the other one though is the better one. So that's actually a better shot. Over time, and with the proper techniques, we can tease more data out of this one than the previous one. And that's what I wanted to show you there. Now, I'm going to go to one more object here.
So, for like, okay, you said if you did like 25 pictures of this,
yes,
would they all be at 20 seconds, and would they all be at like 12,800, or would you do like, you know, 5,000, 10,000, 15,000, 20,000?
You know what? That's a
but all for 20 seconds?
That's a very intelligent question. And the reason it's intelligent is because of the fact that in order to keep
never do that.
in order to keep things the same with this kind of thing, you do indeed. I'm gonna change the battery now. You do indeed want to keep the exposure and the settings for the ISO or sensitivity the same. You have to do that. If you don't, then you end up with a big problem, and that problem is that you don't know where the settings are for different speeds. You don't know how the chip's going to react in the camera, and you need to be able to gauge that. You need to be able to have that. You need to be able to do that. You need to be able to gauge that setting. And if you can't, then when you go to add these images together, you're going to have inconsistencies in the way it goes together, and that's not good. You can't have that, you know.
Well, that's what I was wondering. Like, if you kept raising it in increments of like 1,000 or 5,000 or something,
yes,
but didn't move the telescope and kept it all at say 20 seconds, would that be a help or a hindrance? Like,
it'd be a
because
hindrance.
you'd be bringing in different portions of data, right? But then does it all just get muddled when you try to stack it?
No, see, that's the thing.
Stacking really
depends on being able to have exposures that are all the same with the same sensitivity settings. Because when you take your dark frames, that is all those dark areas, you know, not dark areas, but the modeling I was looking at, a dark frame is going to show some of that modeling, and you want to be able to get rid of that. To get rid of it, it has to be at the same, at the same level. You know, that is to say, the same amount. And to do that, you have to make sure it's the same sensitivity setting and the same exposure time. So that's what has to happen there, you know.
Yeah, because then I was going to reverse it and say, could you leave it at like 12:8 and just go like 5 seconds, 10 seconds, 15, but the same thing.
See, for doing
the other,
for doing the sky tour, I can do that. Okay, because none of the images, other than you know, these I'm doing here, none of these images are actually images meant to make a final, absolutely stunning, gorgeous piece. Okay, to do that, I would have to basically, you know, say to you, hey, we were supposed to stream tonight, but instead I'm gonna do some stuff for myself, and then, you know, go out here and take like, you know, 40 or 50 photos and focus basically on 1 or 2 objects at the most, and then make a stunning object from those. All right, and I would take these pictures very differently than I am now. I wouldn't just take like, you know, 20-second shots or whatever. I might take 5-minute shots at a very low ASA, and have a guider that guides these, you know, guides the telescope very, very precisely. That's something that, you know, we need here at John Zach Memorial Observatory, and that's something we're going to get. But for now, I'm just gonna do this as I go here. Now what I'm going to do is I'm going to take us to another object in our tour of the nebulae
And we actually have a question from Mario.
Oh, cool.
Hi,
Hi, Mario.
Mario.
How you doing?
Can the dark frames actually be different photos, or can one be used and pasted, etc.?
Yeah, the dark frames, you have to use separate ones. And the reason is you want to kind of average out the noise that you're getting. If you don't average out the noise, then you're just doing the same effect. You're doing the same thing on the frame, and you don't want to do that. All right. So yes, it can't be the same, Mario. Mario's excited about astronomy again. I'm proud to say that SkyTour LiveStream has sort of become his second home. Am I right, Mario? Let the chat know that. If it's true. If it's not true, also say that I'm all washed up and I have no clue what I'm talking about. Let me go here to do an acquisition shot.
We're looking for Mario to confirm or deny. Is this fake news?
Yeah, see if I'm faking it or not. I don't know. I believe that he's very happy with the SkyTour.
No, well, like I was saying, I don't post too much in the SkyTour LiveStream Facebook group.
Yeah.
Because Mark kind of handles it, and if he posts something, I'll link it in there. But Mario's always a name I always see, either with a nice comment or with a thumbs up or something. So we appreciate that. I did throw the link in, but please do come over to Facebook. It's the same as on YouTube. It's SkyTour LiveStream with Mark Antonio. And as long as you're nice, I'll let you in.
Oh,
and all the pictures he takes during the streams will eventually show up there, so you can check them out, check out your favorites, download them, stack them, do your own experiments, and you know, even if you do your own experiments with the pictures and stuff, your own stacking or whatever, send us a copy.
Absolutely.
Love to see what you guys are up to. Post that on Facebook.
Absolutely, that sounds like a great idea. By the way, I just wanted to take a moment to say that sometimes things aren't always as smooth at SkyTour than as they may appear. The other night,
oh yes,
the other night I was actually supposed to stream. I wanted to stream, and so I came online, not online, but I came up ready to stream. Got out here, opened up the dome, and I heard a crash. And this massive crash was the dome opening, the slit, the shutter, okay? And it actually literally cracked off the building and fell to the ground, and I was absolutely really terrified that I might have actually destroyed something. So I ran out there and picked the shutter up off the ground. It was actually not too exciting, to be honest. I was a little bit worried that I was going to end up having a big problem here. And what I did was I got someone to help me, and we managed to put the dome back on, that is to say the shutter back in place. And it was really a little bit worrisome, frankly. I didn't know whether it was going to survive or not. But it did, and I was happy that it did. Okay, I'm having a strange issue here.
What is the strange issue?
Well, you see how everything's moving right now?
Yes.
Yeah, I don't know why it's doing that. It should not be doing that.
You're not moving it?
No, it's a collision with the Wi-Fi for some reason. So I have to stop it right now. That was really weird. Okay.
That was weird. I don't know. I assumed you were looking for something and just making some little adjustments.
No, I actually was suffering a failure in here, which I'm not too worried about it at this point. I just need to actually move it around a little bit.
What if there's a ghost in your dome?
Well, that would truly be a ghost in the machine, wouldn't it?
Hmm?
Okay, so now we're going to go up here again.
I wonder if it's a Canadian ghost. If so, you have nothing to worry about.
Right, eh?
Yeah.
That's the old A
Does it
thing.
smell like maple syrup in there?
Oh, how terribly bad. Not even a good joke. No, it doesn't smell like maple syrup in here.
Give him 30 seconds, I'll laugh.
Oh, okay, if you say so. Wah, wah, wah. Alrighty, alrighty. Let me just bring this up here to there, and let's go over. Here we go. That's what I wanted. That was my original target. I'm doing.
I don't know if it's the filter you're using, but it looks like there's an awful lot of blue.
That's the filter in part, but I'm also actually gonna do something else here. This is let me see where I'm looking here and make sure I get this. It is a filter, but I want to move over a little bit. There's Alcyone.
Yeah, whatever filter you're using tonight I like, because the red in the Eagle, that was really bright too.
Yes, it was. It's really
like
pretty.
I noticed some of the ones you used, either the red would be nice and the blue wouldn't, or vice versa, but
Yes.
this one, all the colors are really nice and strong.
Yep, that's exactly what this one's for. Very good one. All right, let's take, let me see. There we got those, that's facing behind, okay, so I go this way. Okay, let's try. Alright, I'm going to do an exposure here at, oh, I'm actually recording that, sorry. Okay, let's do 20,000 for 20 seconds right here. I want to try and pull out some of this blue reflection nebula that are around the Pleiades stars. This is the Pleiades, by the way. Not that I guess I should have told you, but this is the Pleiades.
Yeah, Daryl guessed that.
What's that?
Daryl asked if that's what, if it's
Yep.
we were going to the Pleiades.
Well, when I said Alcyone, or Alcyone, he actually probably knew. He probably knew before, because when you see the Alcyone, it's actually a very interesting, 4 stars right there in the center that you see. Which is interesting, because the other place we see 4 stars in close proximity to each other is in one other famous nebula. And which nebula is that?
Can you repeat the question? I'll type it in.
Well, they'll hear it and they'll respond. I was saying there's another nebula that's very famous for having these 4 particular stars, just like we see here in the middle of the screen with Alcyone. What is that constellation? Not constellation. What is that famous nebula that has what's going on here?
Daryl has a guess. He guessed before I even got the question in. I don't even know if my question makes sense or not.
Okay, well, maybe.
We have 2 guesses that are the same, and
Okay.
one person admitting to cheating.
Well, I don't know how you can cheat this one, because, I guess you could look it up.
They're waiting for Daryl's answer to show up. That's what I would do.
Well,
Is it the trapezium?
Yes, it's actually the trapezium.
Yeah.
The trapezium are 4 stars that formed in the heart of the Orion Nebula. They're actually very interesting because they're hot young stars, and we see some interesting stars, and there's some interesting features in the Orion Nebula and other nebulae like the Orion Nebula that are like the early stars in formation. Okay, now the trapezium stars are already there; they're already formed, but the stars that are formed, okay, you can see that's actually fairly bright blue. You can see some of the nebular detail, but not as much as I'd like. There's in this particular view, and there's a wispy nature to this that actually I'd love to show, and I'm not catching it here. I think that's the reason for that is that I'm not doing this right. Problem is that I'm trying to get my telescope to connect properly to the Wi-Fi again, and it didn't want to for some reason. It wanted to continue. Actually, you know what I'll do? I'm gonna try something else. I'm gonna quit the app and then come back. Okay, so now.
Oh, and just so chat knows, the construction workers are back. They're
yes, that's correct.
Ripping up / repairing the roads yet again.
Yes.
Or continuing, I don't know. I thought they were done a while ago.
Yeah, me too. And that's unfortunate, but that's exactly what we got here.
I'm wondering if could that cause any interference? Maybe not. I don't know.
No, it wouldn't cause interference, but it definitely is no fun.
I was trying to give you a way out. Blame it on the construction workers.
No, the noise is the noise. It's not my fault. Okay, now let's try this.
Yeah, but no, a few people got that. Daryl said trapezium, and Shiver Canada, hello, said Orion trapezoid, and Mario said it was in Orion as well.
Yep.
So.
And he is right. You guys are good, let me tell y'all. I'm trying to tell you. Very, very good. Okay, now let's see.
I mean, the name sounds familiar. I'm sure we've seen this before, but no. Never in a million years would I've guessed that.
Okay. That's okay. I mean, well, maybe if you had a million years, I think you might have guessed it. Okay.
Several more SkyTour live streams anyway.
You need a few more.
A few more.
Just a few. Okay. I'm going to do one more shot like this. Just to try this. And I'm going to go up to 40,000 ASA. And I'm going to drop it to 13 seconds. To see if this will give me what I want. There's something particular I'm trying to get here. And the filter I'm using might actually prevent it from showing very well. So I apologize ahead of time if that's the case. And with the dome pointed this way, besides the stiff cold wind coming in through the opening, you do also hear the noise of the street coming through.
I haven't. I was just hoping maybe we could blame the Wi-Fi issues on them.
Oh, yeah, no. I wish so.
No,
Okay.
I don't hear any construction. I don't hear any crickets. Nothing. You're coming in nice and clear. I'm probably overpowering you as usual. Sorry, guys. I don't know what to do.
Well, actually, the problem is mine. I need another mixer in here that will allow me to actually
turn me down.
Well, yeah, literally. I mean, I got to be able to turn you down because you're not. It's not that you're too loud. It's just that I'm probably too soft. If I was louder, then we'd sound equal and be better. But we don't have that ability. Okay.
Mario wants to know what kind of filter you're using tonight.
I'm using a Skyglow filter, Mario. It's actually a filter that will get rid of the sodium and mercury vapor lamp spectral responses so that I get rid of the glow in the sky. Now, it really means that I have to expose the images a little bit longer. It could also be the reason why we don't quite see the blue reflection nebula like I normally could. But I really do want to use it because that's the only way that you can get rid of something that you may not even think is a problem until it's actually upon you, and then all of a sudden you're using it and you go, whoa, that doesn't look good, you know, that kind of thing. So, you know.
Yeah, it's funny because actually Daryl asked right after that, I wonder if the filter may be hindering seeing the nebulosity in this case.
I believe he's correct. You know, that's what I was saying it because.
Well, I think we kind of took a detour into nebulas tonight just because the
Well, there's no moon.
Dark Nebulas came up, right? So
Well,
yeah, but maybe you weren't planning on staying that long on nebulas, or
no,
things came up.
There's no moon, so it's really nice to do the new nebula.
Mm-hmm.
Well, you know what I want to do though? I want to do this. I want to find this for us. I want to just go look at this.
Are we gonna see the trapezoid better? Trapezoid? Are we gonna see the trapezoid
are we
better?
See that? No, I don't think so.
No. Okay.
Because the trapezium isn't going to rise for quite a while. But I want to take us to this other object in the sky. And here we go. It's actually not that low. It's actually in a pretty good spot. And it's another example of a planetary nebula, like I talked about. And so I do want to try and acquire it here. So let me do this 4K view, see if it'll show. It's really, really faint. Oh, but there it is. Faint as it is. It's large. It's not small. Okay, or closing this application before seemed to have done the job. So now I'm not getting it to just hang in one direction, meaning the telescope is behaving itself. Okay, let's try an acquisition shot here. We're going to go 32,000. No, that's not 32,000. That's 320,000. That won't work. Let's do, yeah, that's quite a ways. Okay, let's go 25,600 for 13 seconds. We're just going to try and get to this. This particular nebula, and I did capture shots of it before, earlier in a different time, and it was really not that good, and I was really disappointed with it. So let's see if I can do any better with it now. All right, and you'll say, well, wait, what nebula are we looking at? We're looking at a planetary nebula that is a dying star, or a dead star, with a white dwarf remnant in the center. But this one, oh, there it is, right in the center. Holy cow. Now, I don't know if you can see that. All right. Again, with this filter, it makes it look blue, but it's actually stands out quite well. This is what's called the Helix Nebula. All right. And the helix is actually very faint. Now, why is it faint? It's faint because of the fact that it's expanded out from the center quite a bit, and the stellar material is beginning to disperse in the interstellar medium. Now, it's actually only 790 light years away, so it's kind of close, planetary nebula-wise, but it's actually just got a really, really cool look to it. And it wasn't really, it wasn't really found by early astronomers. They didn't really catch it because it's so extensive. It's very big. But this time, we can see it now. And I did my acquisition shot here was what was it? Let's see, 13 seconds at 25,600. Okay, so I'll bet you if I go down a stop or two, the 16,000, but then I go up to say 30 seconds, I'll bet you we're going to see a little bit more. Now, why would I drop down the sensitivity? Shouldn't I go up? Well, sure, if you want to capture the coarse object, yeah, dropping it down, or increasing the sensitivity will do it. But it also increases the noise. Remember the modeling we saw? And so you want to eliminate the modeling as best you can, and this is how you do it. You do it by playing the game of dropping down the sensitivity, increasing the exposure a little bit. And most cameras, like this one, you get to 30 seconds, and that's the maximum that they will do, just timed by themselves. There's no cameras that say, okay, take a 1-minute exposure. Yes, all cameras can do that, especially the digital single lens reflex, the DSLRs. Okay, but these cameras will do that with a remote, a remote that you attach, or you do it using a timer. Now, the timer that this camera can use is the iPad or an iPhone, and you can connect to it with Wi-Fi, and you can control it with Wi-Fi. All right. So now look at this object. It's low surface brightness, very, very low surface brightness. So you can barely see it there, but there it is. Okay, and there's that central star right dead center in the middle of it. Again, a white dwarf that's very, with its ultraviolet radiation is just illuminating enough of this to cause it to glow. Just incredible. And now, again, those are the outer shell. That's an outer shell of a star. And the progenitor star, the star that actually caused this, was probably a few solar masses, and when it started to leach this stuff out into the interstellar medium, and then shrunk down again, it became your typical white dwarf, and because that's the core that's left. And as I said, the white dwarf doesn't have any fusion going on of its own. In rare cases, you can have something going on at the surface that is just oddly strange, but this is one of the reasons that it's so faint is because it's so close to us, actually. And at 800, just under 800 light years, being this close, it's pretty big. Okay, but we can at least see it. And if we stack something like this, we'd have to stack quite a few of these to get them to actually look pretty reasonable. Now the other thing is, from this location here, the helix is actually at around a 35 or 40 degree, not even, but I'd say, what is this? It's actually from the horizon, it's about 35 degrees up. Okay, not that high. So we have that going on too, and we're looking through more air, okay, to see it. If it's at the zenith, and if I was in, I don't know, Arizona, well, then it would be higher in the sky. Maybe by, I don't know, about 20 degrees or so higher in the sky, and that could make all the difference. But the Helix Nebula at 790 light years away is the dead star remnant in the center there, the white dwarf, and the nebula associated with it. So there it is, the helix. And again, not very impressive, but it is notoriously hard to see. The first time I ever saw it was right here in the John Zach Memorial Observatory for the very first time. And that was only about a month ago. And it was pretty cool. Now we're going to go to one more object just above it, which I think you'll enjoy. Okay, now let's come up and come over. All right, now let's pop in up close. Okay, this is an object that's very interesting. I'm going to drop down the exposure because I can. Or no.
Yeah, I saw a lot of red pixelation.
Yeah, that's actually just the noise from the ISO being so high. But I'm going to go only to an ISO of 1000, and I'm going to drop the exposure down to like 8 seconds. And you'll see something a little bit more than you see on the screen there, but not too terribly much. Okay, and then I'll tell you what it is. Do you have any guesses?
I don't have a guess as of yet. I don't see anything in chat. I'll keep my eye out.
Okay.
Well,
let's take a look.
But is it a nebula, did you say?
No, take a look at it.
Is it a planet?
Oh, you tell me. You tell me.
Okay, Daryl has a guess. Well, I was thinking one thing.
Okay.
When I first saw the one star.
Yeah.
But then it flashed, and I could see 4 stars, like 2 on either side of it. So then I was thinking something else.
Okay.
And then, as you said, notice the color. I did notice the color. So now I have several guesses, and I think they're all wrong.
Well, you've got to have a little more faith in yourself than that. Okay.
Well,
all right.
is it the Cat's Eye Nebula?
No, Cat's Eye is a little bit bigger than this, but good guess.
Ooh, no, that was Daryl's guess.
Oh, Daryl, I'm sorry. But you know what? I mean, I'm hardly giving you anything to go on.
Okay,
but
is it a
he's
nebula?
right. He is right. It's not a nebula, no.
No.
He is right, though, that, you know, the Cat's Eye Nebula is definitely that color, that particular color.
Well, so is Neptune.
Yes, it is. And that's what it is.
Is it Neptune?
It is.
I swear to God, when I saw the color, I was thinking that's the color of Neptune. But then I was like, are those moons that I'm seeing? Because at first I was, okay, first I saw the color, and I thought maybe it's Vega, because it looks kind of blue. But then when I saw what I thought could possibly be moons or stars, then I was thinking maybe it's Jupiter, and those are the 4 Galilean moons. And I was thinking, wow, that's really incredible to get them all so big and bright.
And to see them
then
when
just
Jupiter's
as I saw the
set.
color, when it came into focus and you said, look at the color,
Yeah.
that's why I said, first I said, is it a nebula? Because I was thinking, if it's Neptune, that's a planet. And I thought you were saying that we were going to a nebula. I swear to God, I thought it was Neptune. Wow.
Yeah. Well, there you go. That's Neptune.
I'm so happy.
No, you
Sorry
get
for the rant, guys. Yay!
No, you got it. And then to the upper left there, that thing that looks like a star. Okay, that's
Like
actually
trident?
Nereid. That's actually the moon Nereid. Okay, and the object that's above Neptune, straight up, that is a star. Okay, the thing to the left that's brighter, that's Nereid. Nereid's actually brighter than that star to the upper right that you see there. Isn't that cool?
That is very cool.
Yeah, you're looking at the farthest planet in our solar system by definition. Okay, and that's 30 astronomical units away, and between that distance and 50 astronomical units is that Kuiper belt, you know, that we talk about so often, where we have a lot of dark planetary type objects, planetoids, and more asteroids for sure, some comets, and then beyond that is the Oort cloud, which is that basically spherical mass of clouds and so forth around our solar system that was pretty much where the comets come from. Now I want to do a one high exposure. I'm going to go and do a 12,800 at 15 seconds. So here I go. Pink. When the screen goes dark, that's what you see. Stars disappear. The planetary system disappears. My feet are getting cold, guys, so I'm going to be terminating here in a little while. I think I did about 2 hours, didn't I?
Yeah, just a little over, yeah.
Okay, cool.
2 hours.
And we had actually a very productive night. We went to a lot of different nebulae. We learned about reflection nebulae and some bits about the emission nebulae, which are the H2 regions. So that's pretty cool. There we go. Now, let's go in and take a look at another gander here.
So, okay, would it be fair to say that those are the only 3 different kinds of nebulas there are?
In general, I mean, we saw planetary nebulae, okay. So H2 regions, or emission nebulae, are one. Reflection nebulae are another. Totally different processes that make them shine, okay. One's pure reflection, another one is atomic excitation of the atoms in the nebula. And then the planetary nebulae are also emission nebulae as well. They are emitting, though, because of the hot white dwarf that's producing a lot, copious, in fact, amounts of ultraviolet radiation in the center. And that's actually pretty cool, you know. And now,
So, what about Dark Nebula?
What about it?
Is that a 4th, or where does that fall into it?
Well, the Dark Nebula is actually usually a property of one of those other types of nebulae, but generally, Dark Nebulae can stand on their own, as the Barnard catalog of Dark Nebulae will attest. And they will be, the Barnard objects are actually, and many times they're Dark Nebulae. There's many loops in the southern hemisphere that are just they look like snaking loops against the Milky Way, and it's so cool.
Wow.
Yeah, so cool. You know, very impressive.
We need to
though.
find more Australian friends with telescopes.
Oh, I know. Me know. I know. We got to find Australian friends.
I don't think you're gonna lure them with that accent.
Well, no, that wasn't meant to be. Now, if you want to talk Australian, then you have to talk like this. It's like, hey, I've been doing this for 18 years, you know. It's make the way it goes, you know. It's like, I love the universe. I just look up at the sky at night and I think, wow, you know, the people in the northern hemisphere see this the same way I am. You know, it's like, wow, this is incredible. You know, it's like, makes you want to go out and be on a walkabout and just like, you know, take it all in. So anyway, you know, that's.
Well, you know what? There are a few times when an image comes in and you get really, really excited.
Yeah.
And it's kind of like Steve used to get when he saw a tiny little lizard in the middle of the jungle, in the middle of the outback. Do you remember
you mean
that?
Steve
Crocodile Hunter?
Steve Irwin.
Yeah.
Yeah.
He got just as excited finding a little ant crossing the path, and that excitement.
Now this little guy right here, this guy is amazing. He's got so many little tentacles, and he makes his way across the ocean floor, and I can't tell you enough. I want to give one to my daughter Bindi, but I tell you, she won't be able to play with it right. You know, it's like, he was a great guy.
Yeah.
And he got killed by a stingray.
I know. I wasn't gonna bring the show down like that, but
That's you know, it's life, unfortunately. You know.
Well, would you be happy if, I don't know, you were struck by a meteor, dying doing the thing you loved?
Way to go! I see, that's the thing. You know, when people say he died doing what he loved, it's like, well, that's terrible. He died. You know.
I know.
You know.
Not much comfort to his family.
And I gotta
That's what I was thinking, but
the other day when just so you know, by the way, did we see any buffering at all?
No one's mentioned anything. I am kind of watching on Skype.
Because I got my upgrade, so I got 10 times faster service. So
oh yeah,
JZM Observatory is actually a little bit faster. I'm being facetious, it's a lot faster. And so the bottom line is, I had the guy come out the other day, and it was raining and pouring here. And he told me he had to go up on the telephone pole to actually check my box to see what's going on up there. And I said, you sure? It's kind of raining hard. And he said, yeah, I'll go right up. And I watched him try to put the ladder up 2 times. It fell. And then the 3rd time he got up there, he climbed. And it just happened to be, I came up from my office at a certain point afterwards. He was out there for quite a while. And he was up on top of the ladder. I watched him go down the ladder. I had just gotten out of my front porch. I watched him go down the ladder, and all of a sudden, I see him fall. And I hear him, he grabs onto the rung of the ladder. And he's up like 10, 12 feet in the air. Okay, and he's grabbing onto the ladder, and he twists around, hanging on one arm to the point where he couldn't hold on anymore. And he's carrying a lot of heavy equipment. So I see him fall, and I hear crunch, and I hear him scream. And I get in my car, it's pouring rain. I go down to the bottom of the driveway. It's 155 feet away. Okay, and I stop the truck in the road, and I park it kind of a little bit out into the road to prevent anyone coming to go racing by where they might hit him. He's actually lying on the lawn just below the telephone pole, and he's unconscious. And I'm like, oh, no. So I run up to the guy, and I was certified in advanced life-saving, you know, some years back, and I just sort of did a visual survey to see if there was anything out of place, obviously. And he started to move his arms kind of like unconsciously, like people who get knocked out will kind of like flail a little bit. And he was doing that. And I bent down to him and I said, hey, and I saw his name and I called him by his name. I said, this is you? And, you know, he basically just nods a little bit, you know, a little nod. And so I ended up saying, okay, listen, I'm going to call 911, okay? And he nods his head very, very, you know, faintly, yes. And I said, tell me what's hurting. And he says, my back. And I go, okay, what else? Your leg, okay. And he's trying to reach for his leg, and I gently take his arm and say, listen, you can't grab onto things. Don't try to move now, okay? this is most important to you. To make sure that you're not further injured, you have to stay still until the EMTs get here. This is going to be the hardest thing you've had to do. And he kind of just nodded. And at one point, I think he kind of passed out again. And I brought him back. I basically said, to him, come on, wake up, wake up. And I just tapped him gently on the, I kind of rubbed his cheek a little bit to kind of help him along, get that stimulus on his face. And he could feel that, which is good. And he was moving his arm. So the EMTs arrived, and they just like cut his pants off. They got all this just to look at his legs, because one leg was really turned badly underneath him, and it probably broken. And then when they rolled him to put him onto the backboard, after putting a cervical collar on him, they rolled him to put him on the backboard, and I could see he had already had back surgery. I mean, he had a scar on his back, a perfectly vertical scar. Probably had some fusion or some titanium put in. So this poor guy, and he's got a recovery ahead of him. I feel bad for him, but he didn't fix my problem. He didn't actually get to it, and I told the supervisor for Comcast came out and drove to the house here from the city nearby. It's actually the city's like 20 minutes away, 20 miles away, and he said to me, "Oh, we'll get someone out here today. Don't worry." I said, "Listen, I only care about the guy. All right, I don't care. I can get my service. Don't worry. I'm not worried about it." "Oh no, we're gonna get it today." "Okay, whatever. But just make sure you let me know how the guy's doing." "Okay, I want to know how he's doing." All right, we will. Well, the guy they had come out next time, he didn't have to go up the pole at all. It turns out that was it was fruitless. It wasn't going to help out, so sad but true.
I didn't know that part.
Yeah, he didn't have to go to the pole at all. The new guy came out, and he was a genius. He was sitting there saying, "Oh yeah, your 10100 switch is too slow. It's gonna throttle you back, and then you got this, you got that, and we can set up these network right now. Let's get the Wi-Fi running." And then he did all that, and everything was working great for one day. And now I have these really strange things where I have to have a physical connection to the network and a Wi-Fi connection to the network to get it all to work right. The Wi-Fi connection can see my internet, but it can't see my network paths, all the places I have on my network. So I've got 2 servers that I store things for the observatory, and I can't see those with the Wi-Fi, but I can see them with the network connection. But the network connection can't see the internet, but the Wi-Fi can. So it's like, it's like 2 problems for the price of 1. It's two tragedies in one. So anyway, I'll fix all that. Right now it's workable, and I wasn't going to hold up another stream just because of that stuff. That's simple stuff. So anyway, so there's a little bit of the interesting stuff that happened over the past week. And I'm going to go find out if this guy is okay. I think he is, but he's just really, really bad luck on that, let me tell you.
You're going to actually go visit him?
I'll probably go to the hospital, yeah. I'm sure he's still there. I mean, he's got had quite a fall, But
yeah, I was wondering, because, I'd want to make sure he was alright too, but I don't know.
What?
Is that appropriate? You don't know him and he fell on your property, like, what if...
Well, he wasn't on my property. He was actually...
Wow.
He was actually at the street, so he was on town property, But I was just concerned, so I wanted to go check it out, They don't have to see me. His family doesn't have to see me if they don't want to. That's fine. But
No,
I'm just that way. I'm one of those guys that just thinks that, hey, look, I don't care about freaking protocol. I want to know if the guy is okay. I don't care if it's...
No, I know, but you don't want to get too involved and feel like responsible that he...
No, he was responsible. I'm not responsible for what he did. But
I would just feel so bad if I went to visit him. I'd want to visit him all the time, and...
Well, okay, now that's what
I mean, I would feel so bad, what if you walk in and he's, paralyzed?
Well, that's, I was.
Oh, that's true. Not everyone has quite the remarkable story you have.
I was. I mean, it was only 2.5 years ago. I was a quadriplegic and I was blind. You know, I mean, that's something to come back from. That's you know, every little thing is a victory. Every little move, the tiniest little movement of your finger, signifies a victory. You know, and that's just great. You know, I like that. It was great. But you know, it's the way it works. You know, I know people know my story. I'm not gonna tell them again. But it's really one of those things that's yeah, you can't forget it. It sort of changes you. You know. Okay, 15 seconds at 6400 on this object. Oh, I see my son Gabe is home. I can tell because the light for the house went on, the automatic lighting. Okay, processing 15 seconds at 6400. Did I say 6400? We'll see this little object down in the bottom there. Here it is. Look at that thing. This is a globular cluster, and it's one of these clusters that, you know, like I told you before, this is one of those clusters that's, you know, a halo object. They all are the globular clusters. These clusters are actually circling the galactic center from every which way around the galactic hub. Not in the same plane as the stars all orbiting it. They're going in a very different manner. They go down north-south, southeast, northwest, all different angular directions. This is a beautiful little cluster. It's 34,000 light years away, and it's 18 arc minutes across. So you can then figure out at 34,000 light years away, at 18 arc minutes across, you can figure out, if you wish, just how many light years across the cluster is. And if you ever want to learn how to do that again, I'll be happy to show you at some point. But I thought you would kind of like to see this. I'm going to just go up one stop in each direction. So 20 seconds at 8,000 now. Now, see, globular clusters are interesting, and I'll tell you why, and I might have said this before. They represent a very different age range than all the other stars that are in our galactic population. And most of these stars in these globular clusters are exceedingly old. They are called population 2. They are older stars. And the ones that we see most of the time, that like when you look at the night sky, there are most of those are all population 1 stars. Okay? 2 being older, 1 being younger. And so these population 2 stars are very different in their composition. And what that means is they have very few metals. And that, what do we call metals again? To those of you in the chat, you remember stars that are high in metals or low in metals. What's that mean? It means high or low in elements other than hydrogen and helium. All right? No, nitrogen is not a metal. No, carbon is not a metal. But in terms of astronomy, non-hydrogen and helium gas is called metals, metal content. And we measure that. There's a ratio that we can measure the metal content of stars. And basically it's a measure of iron to hydrogen. Okay? And that basically gives us an idea of the content of a star, and if you look that up on Wikipedia or some other thing, you'll see some of the right information there about it. Okay, but that's called chemical abundances, elemental abundances in stars, and if you look those up, you'll find tables that'll describe some of these to you. But if you really want to have a fun time, like we were talking about before, look up the white dwarf. And look at how completely exotic that object is to anything that we know. The white dwarf, all right? And then when you think you've got that one covered, look up the neutron star. And then look at that. Now, a neutron star is nothing more than a higher mass progenitor star that then collapsed a little further than a white dwarf could, because it overcomes that pressure I told you about called the electron degeneracy pressure. Electron pressure, basically the pressure of the atomic bonds. They tend to push back like having a bunch of north poles of the magnets around, you know, and so they resist being pushed closer together, so to speak. And it's not magnetic field that we're talking about, but that's just the analogy. So anyway, that's what happens. It's degeneracy that makes up these degenerate matter makes up the surface of the white dwarf. So it's very, very cool. And, well, very, very hot, actually, and gives off a lot of ultraviolet radiation, which is why the planetary nebulae glow as they do, all right, from the atomic interactions with the high-energy particles, high-energy rays, rather. So that has nothing to do with anything that we're seeing now, so I apologize for that. I just thought that it was interesting. I wanted to show you this. One of these days, we'll take a tour of all the globular clusters, because you see them all over the place. They're everywhere, and they're just wonderful, you know. Now, another nebula to look at is this little guy, and you're going to see it in just a second. Just a second. Let me do my acquisition shot here. Well, I guess that must be you, huh?
Hey.
Let's see here. That may or may not be it. I gotta take a shot here just to see what I got. Let's go down to ASA 12,800 and do a quick 10-second shot. And as I promised, I will take my Eagle Nebula photos that I took and process them for you to show you what they look like processed. And I'll upload those to the SkyTour LiveStream companion site on Facebook to let you try them out and try your hand at them. And I'm wondering where this thing is. Hold on. That's not it, is it? No. That's odd. I must have missed it. Oh, I did. See, that's what happens. Sometimes when I try to go somewhere, I don't actually get to the object I was looking for. And there it is. Now you see it. It's on the screen. It's a little faint. All right.
This is something faint. Looks blue.
Yeah. It is not Neptune.
Actually, Neptune was clearer. How far away is this?
This here?
Yeah.
Well, being that this is a nebula, okay, it's actually it's a planetary nebula in Aquarius, and it is only 3,200 light years away. Now, just imagine, this is a planetary, and so was the helix. You remember how big the helix was on the screen?
Mm-hmm.
Okay, compare the size of the helix to this, all right? And imagine that if this was 790 light years away, it would be a massively bigger object in the sky, okay? And that's unfortunately what we get. You know, we see that these planetaries, and it depends on their age, okay? The older they are, the more they disperse, but then the dimmer they get too, as the star begins to cool down, all right? This here is a famous object known as the Saturn Nebula, okay? And the Saturn Nebula, of course, is named that way for the obvious. It actually has this appearance. All right, as you can see, I'm a little overexposed on it. In fact, you've got to, with these objects, when they're far enough away, you can actually you can actually reduce the the ISO sensitivity, like I just did, to 1250 from 10,000, and it should be around a tenth as bright. All right, I did 10 seconds again. So let's see what this looks like. I want to see if we can see any details inside the nebula. Okay, so that's what we're going to do. We're going to check it out now. Let's see what we got. Can we see any details yet? Well, yeah, we can kind of see now there's sort of a darkish lane in the center. Okay. And let's drop the time down by 2 stops. That is two. That's from 6 seconds, from 10 seconds to 6 seconds, at 1250 ISO. And let's see if we can get any more detail in that center section. One thing I'm going to add to the JZM Observatory is we're going to add a ability to do close-up work. So objects like this, we will be able to basically zoom into them very, very deeply and actually be able to see them much closer. Okay, so that's another thing we're going to do. Alright, this is the most recent one right here, I think. And that'll be fun. Okay. Okay, now you'll see that this is actually a pretty good shot, believe it or not, because you can actually see there's a central, fairly thick area, and then there's a little wispy top to it. You see, just off the top, there's sort of a wispy little cloudy thing there. Okay, that's actually there. That's a real artifact on the nebula that's in the nebula, and we still can't see the central star. We've overwhelmed it with the exposure. So let's take the exposure down to 4 seconds at 1250 and see what we get. Very cold. Okay, now let's do this and jump in and how's that look? Oh, we're losing detail on the outside. Okay, I'll have to make this a target for my zoom when I get to do the zoom thing.
Well, it looked like I could see. Well, I mean, it looked like I could see that kind of half circle coming up above it, and it looked like I could see a wisp of a ring going around it.
Yeah.
I mean, that's pretty good detail.
Yeah, that wasn't. Yeah, in the earlier shot, I think we could. All right. Let's see. There we got that. Okay. What else is coming here? What else do I have on the eastern horizon? Do I have anything that I can show you guys? Oh. Huh. Well, we can try this, but it may be in too much haze. I'm going to go for it. We're going to go. Here we go. So just a minute.
Traveling quite a bit for this one.
What'd you say?
We're traveling quite a bit for this one.
Yes, this one is just rising.
And when you say it might be in the haze, do you mean the murk?
It's in the murk, yep.
No, just in case it was a different term.
Just in case what?
Maybe in case it's a different term, like.
Oh,
maybe
where'd you go? You're.
Oh, is that better?
Yeah, no, you're just away from the mic for some reason. I'm doing 8 seconds at 10,000 ASA on this one, or ISO sensitivity, just to see if I can see it. It'll get far better as the season commences. I didn't see it. It's also notoriously dim. Yeah, I'm not seeing it. Alright, let me try 8 seconds at 40,000 to see if I can actually see it.
Okay, while you're looking for that, actually, Ronald just got here and he has a question. He said he saw on the astronomy picture site, so I'm assuming he means SkyTour LiveStream on Facebook.
Yep.
He said it was a picture of an ice ring around a star and wants to know how this happens. Is that something you posted, or?
Was that on the SkyTour LiveStream site?
Formal halt.
Oh, Fomalhaut. Yeah, okay. I thought he was talking about that. Yeah, Fomalhaut. Okay, we can't see this. I was looking for the Crab Nebula, which is another supernova remnant.
Oh, yeah,
and
you said we were going to go.
It's too much in the murk. We're going to have to wait for it to, be higher in the sky. And we're going to have to wait, at least I'm going to be out here at 2 in the morning. We won't be able to see it up high. So I apologize for that.
Okay, well, while you're here, though, David Schmidt actually wants to know what the red object is at 3 o'clock.
Oh, actually, and the other thing is, I've got all kinds of dew on my lens. It was supposed to, what red object? On this view?
Yeah.
Yeah, that's not the crab. I don't believe. Actually, no, it's just it's a modeling from the dew. I've got dew on my lens, guys, so I could take out the hairdryer, but I'm also aiming it right toward the area where the wind comes out. So I gotta turn this the other way because I am really. It's really made me cold. Ugh. I don't know, David. See, this is. I've got like I said, I've got dew on the lens, so I've actually got to take out my dryer, and I've got to run it for just a couple seconds to clear the dew, and then I got to preserve the optics by.
Well, see, I see. It looks like a red star or something.
Yeah, I think Dave is talking about there seems to be an object there, but I mean, it might be. It might be what we think it is. It might be the crab, but we can't tell. Oh, the hairdryer actually went on. I didn't have to beat it to get it to come on this time.
Yay.
Okay.
Okay, so yes, can you tell us about Fomalhaut? Yeah. I know I'm mispronouncing it, I know.
You are, but it's okay.
Fomalhaut?
Let me just clear the dew off here. See, in the wintertime, when this happens on a telescope, it can actually become very, very detrimental. It can actually, freeze, and that's a big problem. You know what I mean? I don't know if you can hear me. Can you hear me okay?
I can hear you. Can you hear me?
Okay, yeah.
That may be the problem.
Oh. Oh boy. Okay. This dew formed on the inside of my corrector plate. So what that means is that that's going to have to be. I'll have to take it. It means that the stuff is seeding on the inside of the corrector plate for some reason, and that means that I've got some kind of crap on the inside that I have to clean off, which means I got to take off the corrector plate, and it's going to be very unfun because it won't take me down at all, but I'll just be stuck. But in any case,
but it's nothing that's going to damage anything inside the telescope.
No, it won't damage anything unless I allow it to. So, what I do want to say though is something else. That is that you know, I really want to tell you guys that I've had the most fun with you. I very much enjoy you coming for this ride with me every single time it's clear. I appreciate your attendance. So tonight, unfortunately, the dew has called the night for us, and I apologize for that. But I hope you guys will give me a thumbs up or two, and subscribe if you haven't yet. Tell all your friends, share it with your friends, and make sure you come back again. And I will answer your questions, and we'll go looking for other things that you want like to find. I want to thank everybody for joining me tonight, and thank you, Amanda, for handling all the in-between questions and moderating for me as usual. Phenomenal job.
Thank you. Good night, chat.
You guys are wonderful, and don't know how to say it, but other than to say that you guys, I love you, man. You're wonderful. So I will see you on the next SkyTour live stream, and I suspect that we'll have a lot more objects to see as the winter approaches. It will get colder. I'll dress warmer, I promise, and we'll check out all the wonderful things winter has to offer. So hey, remember, keep looking up, and good night.